Greetings, this is Professor Roman. We'll continue our lectures on linear algebra. We have discussed the fact that given a linear transformation from V to W, where V and W are finite dimensional, and given an ordered basis for V and an ordered basis for W, we can represent the operator, let's call it tau, by a matrix. And we've been denoting this matrix, by tau B comma C. Okay. If we are willing to ignore the difference between a vector and its coordinate matrix, so let's say tau maps V to W, and B here is a order basis for V, C is an order basis for W. If we're willing to ignore the difference between a vector little v in V and its coordinate matrix, which after all the difference is really mostly notational. Each one determines the other uniquely. And similarly, if we're willing to ignore the difference between a vector in W and its C coordinate matrix, then we can say that this matrix representation of tau is in fact tau, and so application of tau is the same as multiplication by this matrix. That is, of course, subject to this identification here. Okay. So one of the main goals of linear algebra is to find simple looking matrix representations for a linear transformation, so that multiplication by that matrix becomes simple, or at least relatively simple. Now, we're going to have a lot more success, as we've already discussed, with linear transformations from V to W than we are with linear operators on V, because of the requirement, shall we say, that we use the same basis for V on the domain side and on the codomain side. Let's take a closer look at some of this for matrix equivalence and how it relates to matrix equivalence and also matrix similarity. This is our change of representation formula for linear transformations from V to W. Here is the BC matrix representation, and here's the B prime C prime matrix representation, and they're related by this formula. Since change of basis matrices are invertible matrices, and conversely, we can write this equation in this form where P and Q are invertible. P is this change of basis matrix and Q is this change of basis matrix. And this equation motivates this definition that we first encountered in chapter 0. Two matrices A and B are, and I'm going to change this to matrix equivalent, so we're more specific. If there exist invertible matrices P and Q for which B equals PAQ. So if both of the matrices A and B represent the same linear transformation tau, but with respect to possibly different ordered bases, then we have this relationship, and so the two matrix representations, A and B, are matrix equivalent. If two matrices represent the same linear transformation, then they must be equivalent. The converse is also true. Suppose that A and B are equivalent, so P and Q are invertible. And suppose that A represents a certain linear operator tau with respect to the two ordered bases B and C. Then I can replace A by this notation. I'll have this formula. And now all we need to do is find out how we can represent P and Q as the appropriate change of basis matrices. In other words, we want P to be MCC prime. If you go back here, you see why we want that. And we want Q to be MB prime B, because that's the change of basis matrix here. Well, the C and B are given. They're right here. And it's C prime and B prime that we need to find. Well, that was the whole point of theorem 2.52. Namely, given any two, let's say, look at this one, any two of P, C, or C prime, the third item is uniquely determined. Similarly here. So that's exactly what we need to say that these two equations hold, that there are ordered bases C prime and B prime for which these two equations hold, and therefore B can be written this way, and that by the change of representation formula is this matrix, and so B also represents tau. Okay, so here is here's the figure that goes with this theorem. And what's going on here is that we have a linear operator, linear transformation tau from V to W. As we scan through all the possible pairs of ordered bases, one for V and one for W, we will get all the matrix representations of tau. And two matrix representations of the same operator tau are matrix equivalent, and if two matrices are equivalent and one represents tau, so does the other. Therefore, the family of all matrices that represent tau, as we go through the bases, pairs of ordered bases, fills exactly one matrix equivalence class. And this is the theorem in summary. So this says exactly what I just got through saying. This, by the way, shows quite clearly the role of this set of matrices, these J matrices, J, M, N, R, that they are in fact a set of canonical forms, means that there is exactly one J matrix in each matrix equivalence class, which means that every linear transformation from V to W can be represented by a J matrix, and that J matrix is unique. One and only one J matrix. Of course, that raises the question, which J matrix? How do we find a simple method for determining the J matrix that is equivalent to a given linear operator? Or put another way, we need the ordered bases B and C under which the matrix representation for tau is the J matrix. There's a couple of ways we can deal with this. One is to pick any two ordered bases, get the matrix representation for the operator tau. That will be a matrix in this matrix equivalence class. And then the J matrix is easy to find because this, of course, it has to be the same size, so M and N are determined. It's R that we're missing, but R is the rank of the J matrix, and rank is an invariant, and so we can, if we have one matrix in this equivalence class, compute its rank using Gaussian elimination, we get R, we know what the J matrix is. So that's perhaps the most practical approach. Another approach, more theoretical, less practical, is as follows. So what we have is we have a linear transformation from V to W. We're looking for the unique J matrix that is equivalent, that is represented, that's represented by tau. We're looking for the two bases, B and C, under which the matrix representation for tau is this J matrix. So here's what we could do. We could first find an order basis for the kernel of tau and extend it to an ordered basis for the domain V. So I wrote the basis vectors for the kernel as u, k plus 1 through um, the latter part of this, and then B prime is what you would need to add or include in this ordered basis to get a basis for V. So B prime, which is u1 through uk, is an ordered basis for a complement of the kernel. If we could take its image, tau u1 through tau uk, this is an ordered basis for the image of tau. That can be extended to an ordered basis for W. And I'll leave the details for you, but it's pretty clear that tau maps u1 to, if I could call this v1, I suppose, u2 to v2, and so on. And then all these go to 0. So tau is mapping the first basis vector to the first basis vector, second basis vector to the second basis vector, and so on, which means the matrix representation of tau with respect to B double prime and C double prime is a J matrix. You get ones, you get K1s, and then you switch to zeros. I'm not suggesting that this is the most practical approach. From a practical point of view, if all you're interested in is the J matrix, it's simpler to do what I mentioned before, and that is to just find any matrix representation for tau, find its rank, and that will give you the J matrix. But if you want to know the bases the two ordered bases that produce the J matrix, then this is what you might go through. Let's try a similar analysis for linear operators. The change of matrix representation now looks like this. The two outlying matrices here are now related by being inverses of each other. The matrix MCB is called the similarity matrix for this similarity relation. I think I mentioned that before. Hopefully I did. So this equation has this form, where P is a change of basis matrix from C to B. Remember, we have to switch back to the old basis B in order to apply tau sub B. Then we switch back afterwards to the new basis C. So this prompts the definition we have here. Again, we first discussed in chapter 0. Two matrices A and B are similar, denoted this way: if there exists an invertible matrix P for which B equals P inverse AP. Oh, I guess I mentioned it here. P is called the similarity matrix for this similarity. Similarity is an equivalence relation, as we have seen, and the equivalence classes are referred to as similarity classes. So, if we have two matrices A and B that represent the same linear operator, then they are related by this equation, where P is the change of basis matrix, and so the matrices are similar. Conversely, if A and B are similar, and A represents an operator tau with respect to an ordered basis B, then we have this equation, and all we need to do is solve a single matrix equation. We are given P and we are given B, and we need to find C, and again, the theorem, what was it, 252, comes to the rescue. There is a unique ordered basis C for which this holds, therefore B also represents tau, but now with respect to C. The analog of the previous theorem goes like this. It's essentially the same, just a special case. Given a linear operator tau on V, we scan through all the ordered bases for V. We pick up matrix representations. Any two of these are similar, and any matrix similar to one of these also represents tau, and therefore belongs to this family. So this family of matrices that represent the operator tau fills exactly one similarity class. Each operator on tau is represented by the matrices in a single similarity class. Unfortunately, that's where the simple analogy between matrix equivalence and matrix similarity ends, because as we've discussed before, there are no simple sets of canonical forms for matrix similarity. So while the theory may carry over, the practice does not. The rational canonical form is not simple. In theory, there is essentially one matrix from that set of canonical forms. There's a problem with the order of diagonal entries we'll discuss later. But essentially, the rational canonical form is a canonical form. It's not quite a canonical form. We did discuss that, actually, I think, briefly. But the difference, the issues are not important. So we can say in loose terms there is one, better to say essentially one, matrix in so-called rational canonical form in each similarity class. The problem is those matrices are not very pleasant to work with. So that becomes more of a theoretical issue than a practical one. But still, and we will have to devote considerable time to even finding the rational canonical form, which we will do later in the course. Nevertheless, there is one item that is of what you might say constant but minor annoyance, and so this is a reasonable time to discuss it. Consider, for example, a diagonal matrix. If we reorder the entries on the diagonal in any way whatsoever, the resulting matrix will be similar to this matrix. That requires proof, and we'll get to that in a moment. The problem with this, the minor problem with this, we can't avoid it, is that even diagonal matrices then are not going to function as true sets of canonical forms. They can only function up to the reordering of the diagonal elements. Put more succinctly, if a similarity class has one diagonal matrix that is, let's say, at least 2 by 2 size matrices, or at least size 2 by 2. If it has one diagonal matrix that have different entries on the main diagonal, then it's going to have another. You just swap the diagonal elements around. So we don't get exactly one diagonal matrix in each similarity class. So that spoils the precise definition of canonical form. But it's a minor problem, really, so we just have to acknowledge it. In my experience, all the books that I can recall seeing do acknowledge this issue, but I've seldom seen anyone prove that if you reorder the elements on a diagonal, you get a similar matrix. Maybe left as an exercise, and so on. But this problem is a little bit more general than just diagonal matrices. Suppose we have a block diagonal matrix. Then any reordering of the block diagonals will produce a similar matrix. And that's what I want to prove right now. All I need to do to prove that is to prove that if you interchange two blocks, the resulting matrix is similar to the original, because a rearrangement of all the blocks is really just a permutation of these blocks, can be achieved by successive interchanges of two blocks. This is really a result from group theory, which if you decide to look at my group theory videos when I get them done, we will prove that. Frankly, all we need to prove is that we can interchange two adjacent blocks, because the adjacent transpositions also generate all the permutations. But I don't care about it. We don't need to worry about that. So to this end then, let's suppose we have two blocks, Bj and Bk. And here's a figure, and I'm not, even though the figure may look like it, I'm not implying here that those are the only two blocks. There are other blocks. But let's say the block B sub j has column indices p through q, and so row indices also p through q, because this is on the diagonal here. And here's block bk with indices r through s. So as a linear operator, this matrix A sends the standard basis vectors E sub p through E sub q to linear combinations, using the columns here, of those same standard basis vectors, E sub p through E sub q. That's because all these are 0 and all these are 0. And similarly, A sends the standard basis vectors E sub r through E sub s to linear combinations of E sub r through E sub s. So these are, in loose terms, you might say, self-contained. Here is the standard basis then, and I've placed EP through EQ here and ER through ES here. I've indicated them with the braces. Suppose we swap this group of vectors and this group of vectors. So we reorder like this. I think I probably need some more commas in here. Okay. I didn't, these two blocks of vectors may not be adjacent to each other. R may not equal Q plus 1, and the same thing here. Then there may be some other vectors in between. Well, what does the matrix representation of A look like with respect to this new basis? Very simply, you swap these two blocks. The operator A must send E sub p to this linear combination represented by the first column here. It doesn't matter where you put that in the matrix, if in the basis. If you move EP from here to here, it'll just move this column from here to here. So you're just, and it'll also move the row. So that swaps these two blocks. Okay. So the matrix representation of A with respect to B is similar to the matrix representation of A with respect to Sn. These two are similar because they represent the same operator A, but this one is equal to A. So the new matrix is similar to the original. So if you have a block diagonal matrix, and if you permute the indices 1 through m, and then thereby reordering the blocks here, you will get a matrix that is similar to A. Next we come to a very useful fact about similarity, specifically over the real field and the complex field. And that is, frankly, where most of the action takes place in linear algebra. Not all, because sometimes we're interested in vector spaces over other fields, in particular finite fields. But in general, the real field and the complex field are the most important base fields for vector spaces. Suppose that A and B are real matrices, n by n matrices. We can think of these matrices, we can think of any real matrix as a complex matrix that just happens to have real entries. After all, real numbers are complex numbers. This is a point of view that actually will be very valuable, and we'll use it many more times. The obvious reason that it's valuable is that the complex field is algebraically closed, so it's easier to work in that field. The downside, of course, is that we are, in a sense, changing universes from R to C. We work in C, we can't always go back to R. Things we do in the bigger universe do not necessarily hold in the smaller universe. And that is why I'm bringing this up now. So, for example, suppose that these real matrices A and B are similar as complex matrices. That means that B equals P inverse AP for some invertible complex matrix P. Just because A and B are real does not mean P has to be real. So, the question becomes, if A and B are similar as complex matrices, must they also be similar as real matrices, or in the real field? In other words, must there exist a real matrix S for which B equals S inverse AS? It's important to understand the context here before I continue. We upgrade the base field from R to C, and we discover that these two real matrices we had are now similar in the upgraded setting. So P is, all we know about P is that it's invertible and it's complex. It does not have to be real. But this raises the question, is there a real matrix, for a real similarity matrix? So if A and B are similar as complex matrices, are they also similar as real matrices? The answer is yes. And here's the proof. It's quite a clever proof, actually. It's not terribly difficult, but it has a key idea that one might not think of at first. So here's the statement of the theorem. It's a bit simpler to work to avoid the inverses here, is to put the P inverse on the other side and to work with this equation. PB equals AP. And again, our goal is to find a real matrix S for which SB equals AS. Now, P being a complex matrix, of course, can be written as Q plus IR, where Q and R are real matrices. We just split each entry, which is a complex number, into its real and imaginary parts, and then break the matrix up. So this equation that we do know becomes this equation, and we can distribute here a little bit and compare real and imaginary parts and get these two equations, QB equals AQ and RB equals AR. Now, at this point in my lectures in a physical classroom, I stop and I turn to the students and I say, well, are we done? Have we then proven, because Q is real, have we proven then that A and B are similar as real matrices over the real field? And I always get a few people saying yes, and some people saying no. There's a problem. It is true that both R and Q are real matrices, and these are the right equations, but we don't know whether Q or R are invertible, and they need not be invertible. So we can't move the Q to the other side as Q inverse, or same with the R, and we're stuck. So this does not constitute a proof. One has to be very careful to make sure you have covered all of the requirements for similarity. In this case, the matrix Q or R has to be invertible. So we need to work a little harder. And this is where a key idea is going to come in. Of course, if one of Q or R is invertible, we're done. So we can assume that neither one is invertible. So neither Q nor R are invertible. Okay. And we'll take a closer look at these commutativity rules. It really tells us that we can swap Q, but we have to change A to B and so on. Well, all we need to do, and this is a clever observation, is find a real number, little s, for which a linear combination of Q and R, which I call M, Q plus SR, is invertible. Because then we will still be using these two rules. We have MB is Q plus SRB. We distribute the B. Now we can swap both of these around, get this, pull the A out in front, and we get AM. Now we have MB equals AM, and M is now invertible. So we actually need to use both of these commutativity rules. How do we find little s? All we need is one real number for which this is invertible. Well, let's look at this expression, determinant of Q plus XR, as a function of x. This is in fact a polynomial in x. We need to find an x for which this is non-zero. If I call that x little s, then Q plus little sr will be invertible because its determinant is non-zero. The first problem that we face is, could this be the zero polynomial? Could this be zero for all x? Then we're in trouble. But it's not, because even though x is ranging over we're thinking of it as a real variable, we can still formally put x equal I and compute the value of this polynomial. It'll be a complex number. What number will it be? It'll be the determinant of p. Remember p, where did it go here? When p is Q plus IR, right there. Okay. And p is invertible, so this is non-zero. So even though, in a sense, we're not supposed to put in non-real numbers, it's just a polynomial. We can put in anything we want. We put in I, we get non-zero. We know that not all the coefficients of the polynomial can be zero. So p of x is not the zero polynomial, even when we when we restrict x to real values. Not all the coefficients are zero, so it's not the zero polynomial. Well, any non-zero real polynomial has a real non-root. Just think about the graph of a polynomial. It can only cross the x-axis a finite number of times. So there's only a finite number of zeros, therefore there are, in fact, infinitely many non-zeros. And all we need is one of them. So there's a real number, little s, for which p of s is not zero, and so this matrix, q plus little sr, has non-zero determinant, which means that q plus sr is real and non-singular. So A and B are similar over the reals as well. This is a very nice theorem. It's useful, and we will use it. But I especially wanted you to see the proof because I don't recall ever seeing a proof of this theorem in an undergraduate linear algebra book. In fact, I'm not even sure that I've ever seen this theorem stated. Now, don't quote me on that, because I've only seen a handful of undergraduate linear algebra books in my life. But the proof here is a good proof to study. It does have an idea in it, a key idea, and that is forming this polynomial that one might not think of without considerable effort, some insight. And those are the best kinds of proofs. They're frustrating in the sense that you think, well, could I have ever thought of that? But they're enlightening, and it gives you a new technique that might be useful elsewhere, and helps to broaden your imagination in proof making, thinking outside the box, so to speak. We now come to a topic called similarity of operators that is not discussed very often in my experience in undergraduate textbooks, certainly. And it's not something that we are going to need for some time. And then when we do need it, only relatively briefly. So since the book is now available, this book that the videos are based on is now available on my website, I'm not going to go into the details here. I'm just going to give you the summary of what's going on here. As soon as I find the right page. These pages are stuck together. Always very irritating. There we go. Okay. So the upshot of this is a definition and a couple of results that are the analogs of results we've developed for matrices. Let me go back here. Here's the issue. There is a symmetry between the matrices that represent a given linear operator, and we've seen those are all similar matrices, they fill a similarity class, and the linear operators that are represented by a given matrix. So it's the opposite point of view. The point of view we've been taking is we start with a linear operator and we want to find some matrix representations with an eye towards finding the simplest one we can. Now we'll take the opposite point of view. We start with a matrix, and we say, what operators does this matrix represent? We also want to know how two operators that are represented by the same matrix under different bases are related directly. So we have this formula which shows how two matrix representations of the same operator are related. And now we want a formula that would show how two operators that are represented by the same matrix are related. Okay? So, first a definition. Two linear operators, tau and sigma on V, are similar, denoted this way, if there's an automorphism, phi, on V, for which this relation holds. Automorphisms are the analog of invertible matrices. So this is the analog of the definition of similarity of matrices. Now, unfortunately, there's no notation that I'm aware of anyway for denoting the operator that is represented by a given matrix A with respect to an ordered basis B. So I've thought of a couple of different notations. I didn't like any of them. I've kind of settled on this one, which I'm still not crazy about, but it looks a lot like the notation. This is our notation for, just for an operator, or a representation of an operator looks like that. So what I chose for a matrix for the opposite is very similar notation, but I used braces so there'd be no confusion. So this is the linear operator represented by the matrix A under this ordered basis. If two linear operators are represented by the same matrix, but with respect to different ordered bases, then the two operators are similar. And conversely, if two operators are similar, they represent the same, they are represented by the same matrices. Okay? So if we take a matrix, let's see, do I have a picture here? Well, I do sort of. If we take, let's look at this picture. These are the similarity classes for operators. These are the similarity classes for matrices. We've already seen that if we take a single operator, say tau, all of its matrix representations fill a similarity class of matrices. What we are proving, what is proved in this section here, is that if we take a single matrix and we look at all the operators represented by that matrix, we fill a similarity class of operators. And so there is a nice one-to-one correspondence between the similarity classes of operators and the similarity classes of matrices. Every operator in this similarity class is represented by all the matrices in this similarity class, and none others. And every matrix in this similarity class represents all of the operators in this similarity class and no others. So there's a pairing or one-to-one correspondence of similarity classes between operators and matrices. And this should all be satisfying and make some sense, because if we're willing to, again, forgive the difference between a vector and its coordinate matrix, we fix a basis, we're to think of these as the same, and all they are really is different in notation. They both represent a vector and they represent the same vector. Then there should be no reason why there isn't this same correspondence between operators and matrices. They're, in a sense, the same thing.